thanks very much. I'm going to give you a quick overview of ACEMD, its capabilities, and how you go about using it. So, firstly, what is ACEMD? Well, it's a high-performance molecular dynamics code, which we designed specifically for GPU processors. The reason why we use GPUs is because it's a relatively new class of processing device, which is very, very capable at floating point arithmetic, making it a very good high-performance computing processor. And MD simulation is something that fits onto this architecture very efficiently. If you've done MD simulation in the past, then you'll know that in order to do simulations of any useful length, you've had to use more than one CPU. In fact, you probably had to use many nodes on a CPU cluster. And that's quite an expensive proposition. A CPU cluster isn't something that you can buy and run in your own office simply because of the infrastructure that's required to support that. With GPUs, it's possible to do a simulation of a non-trivial length on just a single device. Indeed, if we look at the performance, if we look at the performance of ACEMD on a range of recent GPUs, this is the very familiar DHFR benchmark, then the sort of performance that one gets is of the order of hundreds of nanoseconds a day on just a single device, like the Titan OC here is one of the top cards at the moment. To get this level of performance, hundreds of nanoseconds a day requires maybe 64, 128 or more CPU cores, even modern CPUs. So because this is just a single GPU device, and indeed not even a professional NVIDIA Tesla part, you can see there's a substantial cost saving to be made by using GPUs. Indeed, one would go so far as to say that the sampling problem of MD for many classes of systems is now essentially solved because buying GPUs to do the requisite amount of simulation is a tractable purchase now. So looking at what ACEMD is capable of, well, we support all of the most common force fields one would use for biomolecular simulation, the various variants of charm and the force fields. Also, we support OPLS and Martini and any other force field that uses that functional form and can be the parameter files, parameters of which can be presented in charm or AMBER file formats. So ACEMD natively eats the BDB, PSF, and the charm RDB into PRM files, and also the AMBER PRM top files, which are combined topology and parameter files. As you would expect in any code that one uses for production MD for biosystems, we support PME electrostatics, so Langevin thermostat and barostat, and for outputs, we derive trajectories in XTC and DCD formats. XTC you might not have come across before if you haven't used GROMACS. It's a compressed trajectory form factor, which is very space efficient. Typically has a 30 to 40% saving over saving in the DCD format, which is native to NAMD. Going beyond standard and unbiased MD, we support metadynamics using the very popular FUMED package, which is a third-party package, but it's integrated with ACEMD using the ACEMD extension interface. There are two forms of extension that one can add to ACEMD. First is using scripting in TCL. If you've used NAMD before, then this will be very, very familiar to you. I'll get into these in a bit more detail later, but suffice to say that there's another scheme which is a lower level scheme for which one needs to be programming in C. Lastly, As ACEMD is a commercial product, it comes along with a full support package from the Mafia at Acellera. So what are the requirements for running ACEMD? Well, there are reasonably relatively few of these. The first is that one needs to have a system which has got a modern 64-bit Linux operating system. If you have a Linux system, it's almost certainly 64-bit. The distributions that we formally support are Red Hat 6, or one of the variants like CentOS or Scientific Linux, and Ubuntu 12 and later. You can use any other operating system which is supported by NVIDIA's CUDA, but these are the two which we directly support ourselves. Then, of course, you need a GPU. Well, ACEMD can use any number of GPUs, but in practice, scaling is limited for a single simulation to using up to 3 GPUs in a single simulation. The reason for this is principally because the GPU is so very fast at MD, particularly relative to the amount of I/O bandwidth between the GPU and the host system, that although one can run a simulation over multiple GPUs, the return that one gets is very, very modest, simply because the cost of doing the communication between the cards rapidly comes to dominate relative to the amount of work that's going on the GPU. So, well, that's good news and bad news. The bad news is that the performance that you can expect to get with GPU MD is largely within a factor of 2 of the performance one can get from a single GPU. But the good news is that a single GPU is very, very fast indeed. The type of GPUs that we recommend are the latest 700 series NVIDIA GeForce GPUs, which are very good for desktop or workstation. The 780 and the 780 Ti now is the fastest model. If you're deploying in a large cluster, then the NVIDIA Tesla parts are probably the parts that you would look at as they're more designed for a cluster environment. The ACEMD software itself is a binary distribution, so you don't have to crap about doing any compilation or anything. You can download the package, put it onto a machine, and it's ready to run. That said, a machine like this is something which is perhaps not the run-of-the-mill. You could go to Dell and buy a machine with a GPU, but if you wanted a machine with several GPUs, then your Dell salesman's eyes would light up with dollar signs, and they try and sell you a very impressive and very expensive workstation indeed. So one of the things that we offer is something called the Metrocubo workstation, which is a very high-performance workstation, which is cost-optimized for ACEMD. We choose the components so that the machine, you're effectively putting your money into the components which are most important for the simulation. So we specify with very good GPUs and a single processor and a single high-capacity disk. And this really means that you're getting the most bang for your buck, because you're not spending money unnecessarily on very large amounts of memory or second processors or RAID disk configurations. Furthermore, because we control every aspect of the design, we design the chassis ourselves, we can make sure that this thing cools the GPU very well and so runs very quietly, and makes it appropriate for running this inside a quiet office environment. And these things come pre-installed with the operating system and the software, and they're ready to go out of the box. So, as an ACEMD user, you're not left high and dry when it comes to running the thing. We have plenty of documentation available on our website. We have a collection of manuals running from a user guide. Most of the subsequent material in this presentation will be drawn from this user guide. An installation guide if you happen to be a systems administrator doing an installation on machines with a cluster. An exhaustive command reference, which goes into detail on every command configuration option that's available for ACEMD. And then lastly, a guide for those extension interfaces as I talked about, Metrocubo programming and the C programming. Furthermore, we run an annual workshop here in Barcelona, and you can find the material and presentations for our last one on our website at this link. And just falling off the bottom of the screen is the link for our community forums, where you can post questions which may be of interest to the ACEMD user community. Although you can't see the URL, it's available if you go to the Acellera.com support pages. Okay, so I'm assuming that you have done a small amount of MD before, but it's not your primary expertise. Please correct me if I'm wrong in that assumption. So to give you an overview of what you do when performing MD simulation, well, the first step is to prepare the model. This means finding input structures for the protein and then small molecules, drawing the parameterization of that, and getting producing the files which are necessary inputs to the MD simulation. Once you have these, you have to prepare them before one can do production MD simulation. The models that come out of the build tools need energy minimization and equilibration to the right starting conditions. Once you have accomplished that, then you're ready to start to do production MD, which is where the bulk of the simulation occurs. Then, whilst that is progressing, or perhaps at the end of your simulations, you would analyze the data. So I'll go into each one of these topics in a little bit more detail now. So to prepare a model, well, first, it's assumed that you want to do a ligand binding simulation. So you're looking at perhaps the binding process of a small molecule to a globular protein. So first you need to obtain the starting structures of those two objects. The PDB structure of the protein you probably draw from the protein data bank. The small molecule, perhaps you have the 3D structure already. If you have only its 2D structure, then you would need to produce a 3D conformer. Perhaps you use the Open Babel tools to do that. Then the next, probably one of the more important steps, is to choose the force field that you want to use for the simulation. Broadly speaking, there are two families of force fields that one would use for this type of simulation. The first is the amber force field, and the second is the charm force field. Now, if I were to give guidance in choosing a force field, then if you wish to simulate any protein in a membrane, then the charm 36 force field is the force field to use. Otherwise, the amber 12 SB force field represents the best of the amber force fields to use, and it's very good for a globular protein. So, when you are parameterizing the small molecule, this is quite an involved task. The two different force fields have different build tools that one uses to fully parameterize a model, and the processes for parameterizing small molecules are quite different between the two. But broadly, the things that one must be careful to check are that one gets the protonation of the small molecule right, and that for whatever parameters that one gets from the automated parameterization tool, one checks carefully, perhaps with a short simulation, to see whether the behavior of the molecule, if it has any rotatable groups, is as you would expect. Because the way both the amber tool, which is anti-chamber, and the charm tool, CGNFF, work, is to parameterize using a restricted set of parameters and to parameterize the molecule by analogy. So one can often, it's not difficult at all to find a structure that these fail to parameterize well. So one should always check very carefully before investing a large amount of simulation time in a model which is poorly parameterized. Anyway, I digress. But once one has the parameterization of the small molecule, then one needs to prepare the protein. This probably the most important aspect of doing this is to correctly choose the protonation states of the protein. Again, largely one has to use one's own chemical intuition in doing this. There are automated services like the H++ web server, which will have a stab at doing this for you. But it's pretty important that you check any results that gives you, perhaps by looking at the electrostatic potential of the resultant parameterization in VMD, which is a very good visualization tool. And just making sure that it looks appropriate for the conditions that you want to simulate in. So once you have those two things prepared, then it's a matter of using the build tools which are appropriate for the force field you've chosen. If you are using AMBER, then the best tools are the AMBER tools, which are TLE and its friends. And if you're using CHARM, then what we recommend is that you use CHARM GUI, which is a web service for preparing a model. If your models, of course, are confidential, then you probably can't use an external service. So parameterization for CHARM then means running the PSF gen tools inside the package VND. Anyway, the output of either of those two build chains, after you completely solvated and ionized the system, are a set of files which represent the topology, the connectivity of the molecule, and the force field parameters. So if it's a CHARM model, force field parameters are separate files which are standard library files for the whole force field, and a topology file which is the connectivity of the molecule and the whole system, and that's system specific. If you're building with AMBER, then you have out of TLE a file called a PalmTop file, which contains the topology and the force field parameters combined into one. So this recapitulates much of what I said. Just the force fields we recommend are these selections. These are the tools you choose, probably for building models, and the tricky problem of correctly selecting protonation and parameterization of small molecules. Okay, so the next step after one has built the initial conditions is to equilibrate the model. Well, this is a two-step process. The first is that one needs to perform an energy minimization. So the structure that comes out of the build system is largely correct, but has not been corrected for steric or any energetic collisions between groups, particularly the algorithms used to place ions and to place solvent around a protein do not necessarily anticipate and correct for steric collisions. So an energy minimization is something that one performs to remove these gross mistakes from the model. ACEMD has an energy minimizer built in. You activate it with this keyword minimize. We typically run a few hundred steps of energy minimization just to remove these gross problems. Then you would follow this with a short step of true ND in the NDE ensemble, and this further relaxes the system, ready for the next step, which is a pressure minimization. The reason why you did the short NDE is otherwise there can be some very large energies introduced in the very first steps of the simulation, which can be enough to destabilize the algorithm used to control the pressure, and you see the system explode. So the equilibration is intended to relax the system to the conditions that you want to simulate under. So really, it's a pressure equilibration. And this is best done in two steps. The first is a longish simulation in which you place positional constraints on the small molecules in the system and also the carbon alphas of the protein. And this keeps those two aspects of the system fixed in space whilst the box is the pressure is equilibrating. And this can be quite I wouldn't say a violent process, but some of the conformational changes that the box undergoes during this initial pressure equilibration can be quite dramatic, and that can, if you don't have these constraints, cause unwanted conformational changes in the protein. So you keep these things constrained until the pressure is close to the desired pressure, which would be around 1 atmosphere. You really have to watch this by eye. You would watch the output of ACEMD. You see that the running pressure average gradually approach the set value, and you'd also watch the box volume for a while to make sure that that's converging to a stable quantity. Once that has occurred, then you change to NPT unconstrained, remove those constraints, and allow the protein to relax slightly. And at that point, the equilibration is complete, and you have equilibrated structures which are ready for the production simulation. Typically, we recommend that the production simulations are done in NVT, even if you wish to simulate a membrane system for which pressure control is pretty important. It's better to do, in that case, in case of a membrane system, to do a much longer and more complete NPT equilibration before changing to MVT. The reason for this is that with even the best force fields, very long single simulations for the membrane systems aren't very well controlled by barostatic algorithms, and you can see, unless you impose additional constraints like forcing the pressure tensor to be isotropic, then you can see that the membrane systems tend to fall apart in tens of microseconds. So it's generally better, even in that case, to do all the simulation in MVT. There is also a performance implication for using the barostat because of the additional computation that is needed. MPT simulations are some 20 or 25% slower than the same simulation run at constant pressure. At constant volume. So the production parameters that we generally recommend for MD simulations for those force fields are to use an electrostatic cutoff of 9 angstroms coupled with PME electrostatics, and Langevin thermostat to equilibrate to control temperature, for which we select a very mild coupling constant. We use shape constraints to constrain the fast modes of vibration, which are the bonds to any hydrogen atom. And we use a time step of 4 femtoseconds. If you've done any MD simulation before, you may think this is quite high, because for a long time MD simulations, the best practice, as it were, was to use a time step of no more than 2 femtoseconds. Well, we had some algorithmic modifications in ACEMD, the main one of which is what we term hydrogen mass repartitioning, which allows these simulations to proceed stably with a time step of 4 femtoseconds without any changes to the thermodynamics of the system. We recommend these parameters for just about everyone. We do all of our own simulations, and we've probably done many tens of milliseconds of simulations for our own research using these parameters. Lastly, when it comes to sampling the trajectories, usually we find a sampling frequency of hundreds of picoseconds, 100 picoseconds is adequate. So that's a good compromise between sampling and not oversampling and unnecessarily using storage. Then finally, once one has the production simulations underway, you need a method to analyze the trajectories. You can do this with a whole variety of tools that exist. Some of the best ones are the GROMAX analysis tools, which are command line tools and will analyze your trajectories and report specific quantities. VND is a very powerful graphical analysis package which we use extensively in-house, and I very recommend you use that if you don't already have some preference. There's an awful lot to be said about analysis, and most of it, I'm not going to say any more about analysis because that's a topic in itself. Suffice to say that there are other new and quite powerful analytical techniques, one of which is Markov state modeling, which is something which we're developing extensively in-house now, and we expect to be bringing to market very soon. So, now you have a picture of what it is you want to do. How do you go about driving ACEMD to do these simulations? Well, ACEMD's input is controlled from a single scripted input file, and it has a very simple syntax. You see an example of it here on the left. If you've used NAMD before, then this syntax is very familiar, should be very familiar to you. Broadly, the first word in each line is a command, and then any values following it on the same line are arguments for that command. Any lines which are blank or anything after a hash symbol is ignored as a comment. Probably the most important gotcha in this format is that the commands are case sensitive. They should all be lowercase. And also something which isn't apparent from looking at this is that the input file is actually parsed as a TCL program. So in addition to treating it as a dumb input file like this, one can do quite complex things in this simply by writing a TCL program. So now I'll go over how you run ACEMD, and then we'll look at the input file in a bit more detail, and I'll show you the commands that you need to have in that. So to run ACEMD, simply you run ACEMD from the command line and with an argument input file, which is the name of that input script. If you don't specify input file, then it will assume that it should look for a file called input, and if that's not there in the current directory, then it will just terminate with a help message. If you have a machine with multiple GPUs, then you should specify the GPU that you wish to run with using the argument ---- device, and the GPUs are ordered in your system numerically starting from 0. If you've got 4 GPUs, they're 0, 1, 2, and 3. If you wanted to run a simulation in parallel on more than one GPU, then the syntax is ---- device, and then a comma-separated list of the GPUs to use. For example, 0, 1, 2 will run a simulation on the first 3 GPUs in the system. So, as I said before, there's a very extensive vocabulary for that input file, and it's documented online in our manuals, but also that help is built into ACEMD directly. So if you're writing an input file on your machine and you want quickly to refer to the commands for a particular function, like for example the commands which control TCL scripting or electrostatic configuration, then you can refer to that section of the manual by running ACEMD with ACEMD -command, and then that will give you a list of all of the sections for the manual. ACEMD command section, a section with the name of one of those sections will list all of the commands that pertain to in that section, or you can look up a single command directly by specifying it here. The response to any one of these will be a command followed by the arguments, the valid arguments or range of arguments for the command, and then a description of what that command does. So here is here's an input file. Actually, this is somewhat truncated. There's a line or two missing off the bottom. Actually, it goes over 3 slides because I'm going to cover everything that goes into the input file. So from the top, one needs to specify the input structure, which is the starting coordinates for the simulation. In this case, it's a PDB. You might also have the if you have the coordinates which have come out of an equilibration, then they'll be in a binary format with the suffix .coord or COOR, in which case you specify those with the command bin coordinates, not coordinates. Next, you specify either an input temperature, and this is used to initialize the velocity field for the simulation. Likewise, if it's coming out of simulation coming out of an equilibration, then you can specify the output velocity field from that equilibration as the input here with the command binary velocity. Next, you need to tell the program what the dimensions of the unit cell for the simulation are. Now, I should say ACEMD performs all simulations in a fully periodic space, which is to say the system is replicated in infinite to infinite degree in both X, Y, and Z directions. So you specify the dimensions of the unit cell in angstroms. You can either specify it explicitly with this command cell dimension. The cell must always be cuboid, which is why you see here the X, Y, and Z linear extents. They're scalars, not vectors, because they're aligned with the Cartesian, the normal Cartesian axis. You can also specify this in a file which we call the extended system file, which is something which would be written out again by ACEMD at the end of the simulation, containing a box dimension which may have changed if the simulation was done under constant pressure conditions. Next, you need the parameters for the numerical integrator of the system. Here you set the time step. Falling off the bottom are the 2 commands for setting hydrogen scaling. You have to set that to a factor of 4, and you have to set rigid bonds on if you are to use a time step above 1 bent per second. On the next page, we move over to parameters which directly pertain to the force field. So first we specify, because this is a charm simulation, we have a PSF file and a parameter file. And then these technical parameters here exclude scale 1.4 and 1.4 scaling, relate to how the MD engine treats the interaction between atoms which are at opposite ends of a dihedral term. This relates directly to the functional form of the charm and amber force fields. In practice, these are parameters that, if you're using charm, you always have to have these set. If you're using amber, then you always have these set. 1.4 scaling has a different value. It's 0.833. Switching switching and cut disk refer to how the electrostatic and van der Waals potentials are treated. Here, this means that direct non-bonded interactions are calculated between atoms which are 9 angstroms and less apart, and switching means that that potential is not truncated at 9 angstroms but reduces smoothly to 0 in the range between 7.5 angstroms and 9 angstroms. Again, these are figures which are considered best practice for using these 2 force field classes. Below are the output parameters, where one specifies the name of the output trajectory and also the frequency with which frames are dumped to that trajectory, and also with which diagnostic energy output is printed to the console log during the course of the simulation. Next up, we set the electrostatics here. This is indicating that the particle mesh UL algorithm is used to calculate the electrostatic contribution for atoms which are more than that cutoff of 9 angstroms apart. PME uses a mesh-based algorithm, and the spacing of that mesh, the points in that mesh, represent a trade-off between accuracy and speed of computation. The best practice here is to have a mesh spacing of 1 angstrom, 1 point per angstrom. So if you set grid spacing of 1.0, then ACEMD will work out the optimum mesh size subject to that constraint. Alternatively, you can specify the dimensions explicitly, but probably it's better just to leave it to ACEMD to automate that. The following line, PME frequency 2, indicates that a multiple time stepping algorithm should be used, and that that the PME should be calculated only every other time step. This is an optimization, really. That reduction in frequency of PME allows the simulation to go faster without taking it outside of the acceptable bounds of accuracy. The next section indicates the configuration of the thermostat. Here it's activated with Langevin on. Langevin temperature 300 indicates the set point to which the thermostat should control the temperature throughout the simulation, and below that is the coupling constant 0.1 is the value that you can use here. So there's actually an awful lot that goes into an input file. Quite a lot of it is boilerplate, in that you find yourself using the same stuff over and over again. So what we have is a method which effectively allows you to define macros, which allows you to set a whole bunch of parameters using just one command. And that command is protocol, and we define a set of protocols which are shipped along with ACEMD. Some of them are here. You see there are protocols FF Charm 27, FF Charm 36, FF Amber, and you would use one of those to set all of the commands which are relevant for that force field. Then you would follow that up by using run NVT or run NVT to select the appropriate configuration for the ensemble that you want to simulate in. We also have a few more sophisticated protocols like Equilibration, which do a whole equilibration for you, from the minimization to the MPT steps to some final MVT simulation. If you want to see what these do, then you can run ACEMD with ---- those, and that will print out the whole list of commands that activating each one of those macros expands to. So all of that input file that I showed you just can be replaced by these 3 lines here. First defines the 2 protocols that are to be used. The template the simulation defines the use of the charm force field and an NVT simulation, and then just 3 lines to override default values which were set in those protocols to specify the correct file name for the input structure and for the parameters file, and then to indicate that we actually want to run for 10 nanoseconds, not the default of 100. So the input files actually, although there's an awful lot in them, when it comes to writing them, it can be very, very concise. So as I said before, running ACEMD with that input file is a very straightforward matter. That's all you need to type, and then when it runs, this is representative of the output that you see. So starting from the top, when ACEMD runs, it prints out some boilerplate. It tells you about the license license entitlement that you have, then gives some information about the device on which it's running, Most of this information is technical information which is useful in diagnosing problems, but which you generally won't need to refer to. Any line that has a hash at the beginning is effectively a comment line, and can be ignored. After this point here, where it says configuration, it's getting going and it's starting to set up the model. You should pay attention here to any lines which start with warning in capitals, because that will indicate that there's maybe some problem in the system, or some ACEMD has assumed some default configuration value which may not be appropriate for your system. In this case, it's warning that the charge on the system isn't zero, which is really bad practice, because this means that the PME long-range electrostatics aren't guaranteed to be convergent in this case, so you may start to see simulation artifacts. This is something which will be corrected simply by changing the ionization of the system to add in sufficient counter-ions to neutralize that. So here, this line that begins step, the simulation is now started, and every 1,000 steps or different, if you set the energy frequency value differently, it prints out the energy terms for each component of the force field Hamiltonian. You should really, this is really just diagnostic information to give you an indication that everything's okay. You may want to use some of these figures in some analysis afterwards, but generally speaking, so long as the temperature is remains close and about the set point, you can be reasonably confident that the simulation is proceeding just fine. It will also tell you what the rate of simulation is, and give you an indication of when it should finish the simulation based on current progress. And then finally, when it finishes, it tells you how quickly it ran and gives you the citation. It's straightforward. Once ACEMD is terminated, it's produced a bunch of output files. The first are the trajectory files in XTC or DCD format, depending on what you ask for. We now recommend XTC format, as I said before. It's much more space efficient. It has a slight reduction in numerical precision relative to the double precision uncompressed DCD format, but in practice, the precision is adequate, not just for any analysis that you want to perform on the trajectory, but also for as input for restarting the trajectory or new simulation from one of those things. One thing that catches out some people when they see one of these trajectory files for the first time is that the coordinates that go into this file are unwrapped to the unit cell, which means that waters, for example, will appear to diffuse outwards in a shell, and you'll see the simulation unit cell start off cuboid and then expand out into the shell of water as time progresses. This is quite normal, and simply it is a reflection of the fact that the simulation is being conducted in a fully periodic space. You can correct for this in either during the simulation by specifying the command wrap on in the input file, or post hoc by processing in BNB using the PBC tools to wrap back to the unit cell. The cell dimension is output in this XSC file, and if you are running with the barostat enabled, then the box size will vary continuously throughout the simulation, because that's how the barostat corrects the pressure. So another file, an XST file, is written, and that contains the time history of the unit cell dimensions. Whenever a frame is written to the trajectory file in that case as well, the box dimensions are included there, so you can reconstruct that history on a frame-by-frame basis using just the DCD or the XTC alone. ACEMD simulations are restartable. You simply have to have the command restart on enabled in the input file. And this causes ACEMD to periodically dump at full precision the coordinate and velocity fields of the simulation and some additional state which is required to restart the simulation. So usually what we recommend is that you specify the restart frequency to match that of the trajectory output frequency, so that every time a frame is appended to the trajectory, ACEMD also dump state so that it's possible to restart from that point in the future. The system energies and also output, those I showed you just, they go to the console only. If you want to collect those for posterity, then you need to redirect them to a file. So I've now shown you everything which is necessary for you to get going with ACEMD and to perform basic, unbiased MD simulations. If you want to go a bit further and introduce biasing forces into your simulations, for example, you may want to do something like umbrella sampling, where you may wish just to constrain a ligand in a volume, or perhaps you want to introduce a small biasing force to pin a loop closed, or something like this to constrain some aspect of protein motion. Then you can do this in two ways using the extension programming interface. The first is the Tickle interface, which is very high level and it's very, very easy to use. And it's designed exactly for this, for just applying a small number of forces to a small number of atoms. You use this by writing two. Firstly, you have to be familiar with the Tickle language. Well, this is probably the hardest aspect of programming these extensions, because TCL is a scripting language which perhaps isn't nearly as common now as it was just a few years ago. That said, there's an introduction. There are many good introductions on the web, and we have an introduction in our extensions programming guide as well. So you practice to give a high-level view. You write two functions. The first is to count forces init, which is called by ACEMD at the beginning of the simulation, and in that function you specify the atoms or the groups of atoms that you are interested in modifying during the simulation. And then the second function, count forces, is called every iteration of the simulation, and this is your opportunity to take the positions or the velocities of those particles that you express an interest in, and to calculate and apply the biasing force. So there are plenty of examples of this in our programming guide. The second interface is a lower level one. It's a C interface, so you need to be familiar with programming in that language to use. The reason for using this interface over the TCL1 is if you are calculating a biasing force which is numerically intensive to compute. Tickle is very straightforward to write, but it's pretty slow to do computation in. So if your potential is complex, or if you're applying it to a large number of atoms, then it's much better to write at the C level. Furthermore, if you have an existing biasing tool, like the metadynamics package PUMED, that you wish to interface with ACEMD, this is the level at which you would do that. So that largely concludes the presentation. If you have any questions, please let me